shape memory metals which can revert from one shape to a different one simply by being warmed or otherwise triggered have been useful in a variety of applications as actuators that can control the movement of various devices. Now, the discovery of a new category of shape memory materials made of ceramic rather than of metal could open up a new range of applications, especially for high temperature settings such as actuators inside a jet engine or a deep borehole. The new findings were reported in the journal Nature. Shape memory materials have two distinct shapes and can switch back and forth between them. They can be easily triggered by temperature, mechanical stress, or electric or magnetic fields to change shape in a way that exerts force. They are interesting materials because they are sort of like a solid state piston. In other words, a device that can push against something. But while a piston is an assembly of many parts, a shape memory material is a solid state material that does all of that. It doesn't need a system. It doesn't need many parts. It is just a material and it changes its shape spontaneously. It can do work. So it is interesting as a smart material. Shape memory metals have long been used as simple actuators in a variety of devices but are limited by the achievable service temperatures of the metals used, usually a few hundred degrees Celsius at most. Ceramics can withstand much higher temperatures, sometimes up to thousands of degrees, but are known for their brittleness. Now, the MIT team has found a way to overcome that and produce a ceramic material that can actuate without accumulating damage, thus making it possible for it to function reliably as a shape memory material through many cycles of use. The shape memory materials that are out there in the world, they are all metal. When we change a material shape down at the atomic level, there is a whole lot of damage that can be created. Atoms have to reshuffle and change their structure. And as atoms are moving and reshuffling, it is sort of easy to get them in the wrong spots and create defects and damage the material, which leads them to fatigue and eventually fall apart. We end up with materials that can deform a few times, but then eventually they degrade and they can fall apart. And because metals are so ductile, they are a little more damage resistant. And so the field has really focused on metals because when a metal is damaged on the inside, it can tolerate it. Ceramics, by contrast, don't tolerate damage well at all and normally don't bend but fracture. Zirconia is one that is known to have a shape memory property, but it accumulates damage very easily during a shape memory cycle, a property measured as high hysteresis. The researchers took all of the modern tools of science like computational thermodynamics, phase transformation physics, crystallographic calculations, machine learning, and put all these tools together in a totally new way in order to solve the problem of creating a desired material. The result was a new variation of zirconia. Basically, it is zirconia. It looks and smells and tastes just like zirconia that people already know and use, including like cubic zirconia in jewelry. But some atoms of different elements have been introduced into its structure in a way that alters some of its properties. These elements dissolve into the lattice and they sculpt it and they change that transformation. They make it more gentle at the atomic scale. The hysteresis changed so dramatically that it now resembles that of metals. And the deformation that the material can achieve amounts to about 10%, meaning that a rod of this material could get 10% longer when triggered, enough to do significant work. One common application of shape memory materials is relief valves, where if a tank of something exceeds a certain critical temperature, the valve is triggered by that heat, automatically opening to relieve pressure and prevent explosion. The new ceramic material could now extend that capability to far higher temperature situations than present materials could handle. For example, actuators that direct airflow inside a jet engine might be a useful application. While the overall environment there is hot, there are various channels of airflow being controlled. So those flows could be used to trigger a shape memory ceramic by directing cooler or hotter air on the device as needed. Their team plans to continue exploring the material, finding ways to produce it in bigger batches and more complex shapes, and testing its ability to withstand many cycles of transformation.